Okay, so today we are going to solve the following system of linear differential equation using a numerical solver in the Python environment. Okay, and after we have solved it numerically, the solutions x and y, we're going to plot them on the same axis. Okay, clearly you can see that x and y are functions of t. X is a function of t and y is a function of t. Okay, so you will see that the solution x is also imputed into the y equation. Okay, so this is basically a coupled system. Okay, the parameters alpha and beta are given as a negative 1, and the initial condition of this system is zero point 0.1 for x and negative zero point 0.5 for y. Okay, so we're going to see how to solve this in the Python environment. Okay, so if you don't have, for example, Anaconda Python installed on your computer, you can actually do this directly online. So what you do is you can open up a browser and type collab.google and you hit enter. You can click new notebook. Okay, so here we are. So but I'm going to do it in the environment that we started from. Okay, you can type in a cell. Okay, so have a cell up there, or if you don't have this cell already there, you can actually click plus code to add a code cell. Okay, that is if you don't already have it. Now I have two code cells. I'm just going to remove one of them. Okay, I'm going to remove this one. Okay, let's type in the one above. Okay, now because we need to plot, I'm going to import the plotting library, which is called the matplotlib.pyplot. Okay, so I'm going to import it as plt, and from the scipy library, from scipy.integrate, I want to import the function solve IVP, which is the ODE solver we're going to use to solve this problem. Now let me define an ODE function, ODE fun, as a lambda function. I want it to be consistent with the approach we use for MATLAB. Okay, so I use a placeholder here for the time, the placeholder for time, comma, then the states. Okay, then I'm going to define my system of equation in between these square brackets. But before I continue, I want to talk a little bit on the states, because this is a vector to hold x and y. Let me put that as a comment. States equals a vector of x and y. So this implies that x equals states 0. It states 0 because Python starts indexing from 0 and y is states 1. Okay, you will recall that the difference between this and MATLAB is for MATLAB x was states 1 and y was states 2. Okay, and that is because MATLAB starts indexing from 1 and Python starts indexing from 0. Okay, so this is the 0th slot and this is the 1th slot, or the first slot. Okay, 1 to know is first slot. Okay, okay, now let's proceed. My equation says alpha times x, so I'm going to have here a constant alpha times x, and we have established that x is states 0 plus states y, states 1, which is y. Okay, so we can put a comma there. Okay, now I can do this on the same line, but I want it to look like the original system we have in the mathematical expression. So I'm going to go to the next line and do that. So here I have x plus beta y. So I'm going to say states 0 plus beta times states 1. Okay. Okay. At this point, I don't want to be passing in the parameters alpha and beta. So I'll just take the definition given as -1 and hard code it into the system definition. So I have a -1 there. So this is my system. And just define the system right here as you have it here. Okay, now the next thing I'm going to do now is just to solve the system. So I'm going to say states equals solve IVP is this function right here. You can see I imported it from the SciPy library, and I'm going to pass in the ODE function that I want to solve. Okay, solve IVPs used to solve initial value problems. Okay, in Python ODE problems. So I have 0 to 8. Let's integrate from 0 to 8. Okay, and then our initial conditions are 0.1. Okay, remember for x is 0.1, and the initial condition for y is negative 0.1. So I have 0.1, negative 0.5. Okay, so basically this is all there is to the solution that I seek. Now, if I want to see what the solution looks like, the solution in states looks like, I can call states and then hit the run button and see what it looks like. While this is running, I want to point out quickly that the states here is not the same as the state in the lambda function. Okay, so the state in the lambda function is local to the lambda function. Okay, and it cannot be directly accessible by any variable declared in the global space. So this state right here is different to this one. Okay, so I could have used a different variable name, of course, but because I want to use descriptive name, that's why I'm still using the word states, because the solution of the ODE, what I'm interested in from the solution are the states x and y. Okay, so these are the data that I'm interested in. Okay, so to access this data, I'm going to say states dot t. Okay, so the variable state holds all of these things right here, but I'm interested in just the t and the y. So to access the t, I'm going to say states dot t. If I run this again, it's going to output just the t. See that? Outputting just the t from 0 all the way to 8, automatic time stepping. If I say state.y and I run it again, so it's going to say I'm going to have a 2 by n array. Okay, a 2 by n array where the first row is x and the second row is y. Okay, the solution that we seek, x and y. So we are required to plot uh, x and y on the same axis. Okay, remember this is not MATLAB, so you have to where is the plot function coming from? It's coming from the pyplot. See, that's why we say import matplotlib.pyplot as plt. So the plot function is coming from the matplotlib library. So we have to say plt.plot, then the time states.t, comma states.y. Let me push this back in a little bit. Okay. Then I have, excuse me, then I have a 0 here, comma states.t, comma states.y, the y value. Okay, so now when I hit the run button, another way you can run this, if you don't want to go hitting the run button, you can hold the control key and press enter. Okay, make sure you are in the cell of interest. Hold the control key and press enter. Okay, here you go. So this is our solution for the ODE. You can see we have the x starting from 0.1 and we have the y starting from negative 0.5. Okay, so this is what the solution of that system looks like. Solution of the system. This is what it looks like in graph, and this is what it looks like in code. Okay, thank you for tuning in to this channel. I would encourage you to come back in about a week for more videos. More interesting videos are coming, so please do well to subscribe, like, share. Okay, share with your friends and those that you know would like to learn Python and adaptive control, and of course other forms of control that we are going to be talking about on this channel. And also I'm going to invite a very special guest, a renowned scientist in one of the best companies in the US, to tell us more about adaptive control in time to come. So you don't want to miss it. So subscribe, okay? And turn on the notification bell as well. Okay, bye-bye.